Well, I watch like generic, like Community, like
What?
Community, the TV show.
Oh yeah, that's just hard.
Yeah, it's all like a show like you have to get like people.
Cool. All right, I think we're live. Okay.
Here's like.
All right, it's lecture time. So we launched Kernel over the weekend, and now we're going to lecture about it. So hopefully you all have at least had some time to look at some of the prerequisite lectures that Jan did back during the dark depths of COVID at 4 in the morning. They're actually pretty good for this module. So I'm going to kind of gloss over a couple things, kind of give you just some quick, here's what you actually need to get started, and then we'll dive into some demos. So first thing to remember is that at a glance, kernel is complicated. There's a lot going on. This is going to be like a foreign sort of area for you. At least I know it definitely was to me when I first started out. You finally feel like you get the grips on user land, and then kernel shows up, and it's like, what is even going on? So the big thing just to remember is just quick distinction is just at a glance, user land, user processes, it's unprivileged. You're not accessing hardware directly. You're not messing with other processes. But our kernel can do this. The kernel is basically your bridge to do this, where it's essentially you can talk to your hardware, other processes, manage memory, basically all the fun things that we expect our system to be able to do. And it's required. And so to get really quickly just into the meat of what's going on in this module, essentially we have these things that are called kernel device drivers. And essentially, it's just code that runs in the kernel, specifically in the kernel, so it's in that kernel space. And essentially, we're implementing the interface for some device or thing. And so traditionally, you could think of this as hardware, but it doesn't have to be hardware. You could have a software-only device, for example, a terminal emulator, those kind of different things. And I've given you just a typical little high-level workflow here, where it's essentially just, okay, let me make sure my audio is coming through too. All right, sweet. Basically, user space calls some system call, so open, read, write on some kind of device file. So for example, the example I have here is just echo AB into some dev my device thing, which this would be a device driver loaded into the kernel. And when you do that, the kernel will go, okay, well, what's the file descriptor that you're referencing, and find out that this is a kernel device. And then it will call that driver's read or write callback, which we define in the device as source. I'll show you that in a second. And essentially, the driver's callback then interacts with the device in some way. So for example, you could copy things from the user space, do some information with the data that you've copied over, and then maybe you copy back to user to maybe return some results. Or maybe you could think of in terms of a device, you're getting some state information. Finally, then you just basically control flow continues going on, and then it returns back up that system call path to the user space process. And so really quickly what this looks like, because I think it's important to just have a basic grip, is we have this structure that's called file operations. Note that this is a little bit technically outdated for modern Linux kernel, but the idea is the same, just the syntax is slightly different, where basically we define these entries for the different file operations that our device can have. And specifically right now, I'm talking about what we call character devices. There's other types of kernel device drivers, such for example as block devices or network devices that communicate slightly differently. But in this case, we're just looking at a stream of data. And so we define these operations, open is going to be device open, release, which is you could think of it as closing essentially, which is really the device release function. And these are things that we get to define. I could name these A, B, C, D, E, etc. And essentially, we just have some initialization function as part of this kernel driver that creates this. And so I've given you an example of what a device write function could look like. So in this case, our arguments are going to be the same just because we're defining an interface. So we have our file pointer, buffer, length, offset, and then similarly, So we can copy something from the user. Obviously, if that fails, we want to fault out. Otherwise, we can say, okay, well, we wrote, and here's what we got. And then we return our length back to the process. Anyone have any questions on this? Pretty basic, just good, important to understand, will help you reverse. Cool. Okay. And so in this little bit, I'm just only showing you like read, write, open, right? So you could think of this as just a device that maybe you open it, and then you can maybe read something from it, or you can write things to it, like pretty basic. The thing though is that that's not everything that we need. And to address this problem, we have what's called ioctl. And so the question that I want to raise to the class very quickly is just, why do we have ioctl? Does anyone want to maybe take a stab at this?
Like a general purpose syscaller function that can do multiple things to communicate with the kernel.
Pretty close, actually. So essentially the point was is that we need to have some dedicated interface to maybe interact with this device other than just reading and writing to it. The question that I would fire back to you is, well, I can write to the device. Isn't that communicating with it?
Yeah, you also want to love it.
I would want to do other things, but what's stopping me essentially from just writing various commands to the device and then just forcing the device to figure it out?
This is like giving like a privilege thing, like a security measure.
Kind of, but the device is already running in the kernel. So if we write to it, it's going to fire off this write handler, which is running in the kernel already. And that's the same place where our ioctl is going to be living, or our code to handle ioctl. Use your hand up.
Maybe because it gives you more context as to who's calling.
Yeah, a little bit of who's calling it for sure. And so let's take a pretty simple scenario. So hopefully you've all at least seen or heard of dev TTY at this point. It's basically a device driver that manages a terminal, your terminal device. And when you read to it, you're reading terminal data, and when you write to it, you're writing data to the terminal. Like, so just as like a quick example, like if I echo something into dev TTY, it's going to show up on my screen. And so some programs, though, like they need to do other things with the terminal. For example, like if I open Vim or I open Tmux or like htop or some other beautiful terminal program that like resizes itself dynamically, right? That program needs to know how big my terminal is, for example. And so when we can only read and write to a device like this, it becomes very complicated because then like me being able to just come in here and echo random things into dev TTY becomes difficult because then I have to go, okay, well, what if that thing that I just sent to the TTY is some command that's trying to get information? And then all of a sudden, I'm stuck writing a parser in the kernel where I have to parse all the data that comes in and goes, okay, well, maybe this is that, or maybe this is this. And you could think of this like maybe it's like I have to go like, okay, this is a command sequence and I have to like get the size or something like that. And then like it tries to do things. I don't know why that didn't work. Probably some dumb terminal thing, but the point is that we use ioctl to essentially make these kind of requests possible, because without it, we would have to like maybe like open up some separate interface, maybe like dev TTY size, for example, and then say, okay, well, I want to resize my terminal. I'm going to echo some numbers into that. And then similarly, like you would have to like constantly listen to this device for changes. Like I would have to say, okay, like literally like while true, do this thing where I constantly cat out this device and it's going to return the size of the terminal to me. And then I have to parse and handle those changes. Like that's really annoying. Like having just a busy loop doing this thing, constantly checking. And so we're more intelligent than this. And it turns out that we use ioctl essentially for controlling devices rather than just like getting data back and forth, reading and writing. So like you can consider like a simple webcam, for example, where it's like reading would be like reading the raw frame data from the camera. But what happens if I want to change the frame rate of the camera or the resolution or the exposure, like all these fun little things that we can play with? And so we introduce ioctl for this to basically enable that control plane. So we can say, okay, well, I have an ioctl, and ioctls contain two key components. Who knows what those two key components are? So when I ioctl, I give it some number, right? And then I also give it a pointer to random data. Boom. Question. How do I know that? Because I'm very smart. No, I'm kidding. So if we go to the man page for ioctl, we can find that. Essentially, well, it doesn't show me the full parameters, but you can go also look at bootlit. But essentially, we give it Where is it? Where is it? There we go. We essentially give it some numeric operation, and then we have to give it data. And in the case of how we define like our ioctl handlers, so like I have an example right here. So here's an example of a device ioctl function that I just casually came up with. And our 3 arguments is basically the file pointer, which is essentially, okay, well, like what device we're writing to. Similarly, we give it a command number, and then we give it some argument of data, which is just a pointer to arbitrary data that we want to send it. And so in this case, I have a webcam where it handles 2 ioctl numbers, which is this int cmd right here. And so in this case, we have 1337, which is setting the mode of the camera, and 1338, which is getting the mode of the camera. So you could think, okay, well, setting the mode, I copy the data from the user directly into my mode. So I'm just basically supplying a new structure for the camera, defining its properties. And then to get the mode, I run some function that pulls the hardware to do this, and I define that myself. Question?
Just a kind of clarification for
Mhm.
ioctl, the kernel needs to be able to handle every command that it gets. You can't like define new commands as a user. It has to be all like given to you basically by the kernel.
So there are ways to do that, but it's a little bit out of the scope of what we're doing here. In this case, you're correct into where you write a device driver, it gets loaded into memory, and then you're not going to be modifying it. There are definitely ways to do this at runtime, but it's not necessarily relevant, and that's going to be like your eBPF kind of stuff. It gets complicated very quickly. And then essentially here, like we just have 2 modes, and then we default and say, okay, well, if like any other command number that we give this, it's just going to get rejected. And we could define a whole bunch of these different control sequences. I could have one to like get the exposure, set the exposure. Like you could think back to like when you're first learning how to do object-oriented programming, you define some massive class that's like has tons of getters and setters. It's kind of like that. So similarly, the way that this works like from a user perspective, and so over here on the right, I guess I didn't label this, but this is user code. So we could say, okay, I have some struct of like width, height, and like maybe the frame rate of the camera. So just basically resolution and frame rate. And then if I want to set it, I could have this function that takes in these various parameters, builds the structure, and then just kind of yeets it at the device with ioctl. So down here in main, I open the device for my webcam, and then I call this set webcam mode, which fires off this ioctl to the camera. And then in the actual kernel driver, so in kernel space, we're going to copy the data from the user over and then use it to basically set those hardware properties. Any questions about that process? Cool. So I wanted to jump into some demos just because this stuff is pretty hands-on. It gets pretty annoying pretty quickly. So we've got a couple to go through. So in our demo dojo, we've added 2 new demos. I've got one for ioctl and one for shellcoding. And let's talk about them. So first off, before I completely go down the rabbit hole here, the first thing is that when you're approaching these kernel challenges, just always do them in privilege mode and practice mode. That way you can actually have access to debug the VM. Like imagine trying to do a pwn challenge without GDB. Like sure it's possible, but is it feasible? No. And is it fun? Definitely not. And so just do yourself a favor, just go into practice mode. And so you can use those VM debug commands, because if you try to use them outside practice mode, you'll get like, you are not root, basically. All right. So let's go ahead and spin some stuff up. So let's see, it's a little small. Let's make a new folder, class demo. Do I have a folder called that yet? Nope. All right, good. So really quickly, let's just explore what we're dealing with. So when I ls challenge, you can see that I've got this module, webcam.ko. So this is our kernel device that is going to be loaded into the kernel. And then I've also have the source of it. So really quickly, like this is not a reversing task. Let's look at what this webcam demo is doing. So first off, just classic headers, defining the module. We have a webcam mode structure that I'm just simply saying we have a width and a height. We're making it very, very simple. And then what we've got is our file operation structs. So I have open, release, read, and then ioctl, just because we don't need to be able to write to the webcam. I'm not going to try and write to the webcam to tell it what it's seeing. And if we go back up, open and released or open and closed, just essentially just logging it. Then device read, we are just going to basically print back that we're getting a dummy image to some buffer and return it to the user. So very, very simple. In like a real case, this would be like pulling the webcam, getting all the raw frame data, encoding it in some format, and then throwing it over a wire, essentially. And then we get to our device ioctl, and we've got just a basic little switch statement here that essentially is copying from user or copying to user based on the number. And I've defined these as macros just because that's typically how you're going to see it. Just because like no one wants to try and remember all of these constants, like we're programmers, like we know how to use variables. So in this case, setting mode, similar to the example I just showed off in the slides, is just going to overwrite the mode structure with whatever we give it. And getting the mode is just going to return the mode structure or whatever is there. And so if I go ahead and boot up my VM, we can see this in practice. So if I do VM connect, give that a second to load up. And let's see, I don't think I put anything in the D message. Yeah, so we're loading our out of tree module. I guess I didn't put a message in that said successfully loaded, but we ls/proc, we can see this new device that's called webcam demo. And I've defined a read function. So whenever I read from it, we're going to get that dummy image followed by the current set resolution, which I have initialized just 640 by 480. It's an old webcam, okay? 480p. And that's where this is coming from. Okay, so now the question becomes, okay, well, how are we interacting with this? And there's a number of different ways to do it. Like we can try to do it in Python. Would not recommend using Python. Just save yourself the effort. It's pain. You can do it in C. You can do it in assembly if you really, really want. I would highly recommend writing your code for this module in C because it's going to be like the most painless way to get from point A to point B. However, someone explicitly asked me on the Discord to go over assembly, so we're going to do that. I was given a request, and I will deliver. Well, it's the same as writing it in C. Almost. All right. So let's go ahead and make it. Everyone is debating who asked this question. You can literally look it up in the Discord. It's public information. That being said, this is something you should do after class, or else I will instantly derail myself forever.
Oh, I know who was.
So let's go ahead and make a new assembly file.
Yeah, actually, it's beautiful.
So
I mean, you didn't have to. Sit. That's not a shell.
let's get our classic boilerplate of assembly in. Until syntax, no prefix. Define our start symbol. Tell ourselves that we're in the text section. And let's get started. So I went over it earlier, but what are our 2 steps for performing an ioctl? Like, if we'll go back. Like, what does this set webcam mode function have to do? Or I guess like I do 2 things, but what are the 2 things that need to happen? Yeah. So the something part is the hard part. So sorry.
You give it a command and arguments for that command.
Yeah. So we down here in main, you can see how I'm opening our device driver. And then simply I just make an ioctl to that file descriptor. And the reason, and basically what happens under the hood, just to make things a little bit clear, is that like device drivers are treated a little bit differently than normal files. Essentially, when the kernel detects that we're trying to open something like this, that's what enables us to have those ioctl commands. Like it says, okay, rather than just reading from this like static file, instead it's going to reroute that into our kernel device driver, which we have built out and coded. That's what that .ko file is that's living in my /challenge directory.
So it's like the file descriptor, different thing.
Not necessarily, I wouldn't say different thing. I would say handled differently internally.
That's how it's interpreted.
Yes. Yeah. Yeah. Got it. Okay. So this means that essentially we just have 2 major steps that we need to go over, which is open, and then we have ioctl. And then if you really wanted to, you could also like try to read and write from the device driver in assembly, but like we have the cat command, so I'm not going to bother going over that. And also all of you know how to open, read, and write a file in assembly at this point. you should. You can also use the pwn tool shellcraft to open, read, and write a file if you really don't know how to do it by hand. But, so, in order to do this, we first need to be able to open a file. So, what is the file? So I'm just going to go down here and define a label and put an ASCII Z. One cool little thing is that there's .ASCII and there's .ASCII with a Z at the end, or .ASCIIs.
What's the difference?
The Z one will put a null byte at the end of your string for you. So,
zero.
yeah. So instead of having to do like that little, sorry?
Doesn't string do that as well?
Yes.
So what's the difference between .ASCII?
I actually don't know the difference between .ASCII Z and string. There's probably some weird, bizarre under the hood difference. But that is something you could very easily look up and find out and then report in the class Discord. All right, so we define our path. And we now have to make an open sys call. If we don't remember how to make an open sys call at the top of our head, we head over to Coder or Coder64 or whatever syscall table you want. And we remember, okay, we have arguments that we need to set up. So we have our file name, we have our flags, and we have our mode. And so first thing, let's just go ahead and get our file name in. So that's going into RDI. So we are going to load an effective address into RDI just using rip relative addressing. What did I name that label? Path. So that's our first step. We're just using rip relative addressing to load the address of this string into RDI. Then we're going to just set up the rest of our registers. So we're going to move 2 into RSI. This is the mode for overread write. You can find this also just by using a man page. You could also like use C types in a C file to build it and then see what the number is. You could also like import C types in Python and do it that way. But that's something you'll learn off the top of your head eventually if you do this enough. Then we're going to, let's see. We also want to get rid of RDX. So just when you're opening something, I just always zero out RDX unless I really need to. So let's XOR RDX with itself to zero that out. I can also move 0 into it, but we're trying to be fancy here. And then finally, I just need to put my syscall number in, which is 2 for open. Question from the Twitch chat is it possible to gdb-gef the kernel virtual memory when we call ioctl? Yes. And I will show you how to do that once we get into the handler. So let's put 2 in RAX and make our syscall. And in theory, at this point, we've ran our open syscall. Where does the return value for a syscall go? We asked you this on the midterm. RAX. All right. And so we need that. So we're going to save that off. So I guess we'll put it in R12 for now. We'll find out exactly what register it needs to be in for ioctl in 1 second. But now we're going to make that ioctl call. So I guess like at this point, I generally would probably sanity check myself very quickly. So I would, let's see, let's go to class demo. Let's gcc script.s. Let's call it S. And then I want this to have static and no standard library. Oh, wait, I think I do get the standard library actually. Wait, no, this is just my comments being stupid. So we'll get rid of those two. That's not how I spell lib. There we go. And then all I would do to just confirm this really quick is just to really quickly run strace. And we can see that we have successfully made that open call. So we get that back. All right, sweet. So now that we've done that, we need to make our ioctl call. And so we'll come over here and find ioctl. And we will find out that ioctl is system call number 16. So I think I'm just going to copy this whole row for now, honestly. Let's do that. So we're going to move RAX16 to get that system call number in. And then if I remembered my argument order, but I'm always scatterbrained, so we're also going to put that right above here. Better safe than sorry. So our first argument is going to be that file descriptor. So rather than moving our return value from the open call into R12 and moving from R12 to RDI, we'll just save ourselves some time by moving directly into RDI. Then we have the two fun mystery arguments to ioctl. So let's consult our source code really quick. So we can see that with ioctl, we are expecting our file, which we've done, and then we've got command and arg. And in this case, command is simply that number, the ioctl number, as we call it. There might be a better standardized term for that, but I've always just internalized it as ioctl number. And in this case, we want to set the mode of the webcam. And we know that this is expanding to 1337, essentially just like we defined that up at the top right here. And so that is the ioctl number we want to use to trigger this. Now, in more built out kernel device drivers, you're going to have a lot of ioctl numbers that are generally documented. And so you won't have to just dig through the source code for stuff like this. It'll generally be like a man page that has this kind of information. So we need to get that 1337, double check. Yeah, it is 1337 into our second argument, which is RSI. So we've already got RDI, we've already got RDX. So move RSI 1337. And then finally, we have this last guy, which is unsigned long arg. And so it turns out that when you have one function that needs to interact with the device in a lot of different ways, then you need more control. And so it turns out that arg here is just basically an arbitrary pointer that we supply. And so this pointer could be like a literal string of data. Like it doesn't have to be a pointer. Like for example, like we could say, maybe my ioctl is like, for example, setting the width of the camera. Like, do I really need to supply a pointer to the number 720, or can I just supply the number 720? And so the way that this arg is used is dependent on essentially what you're trying to do. And so that's why we just call it an unsigned long. It's just basically an arbitrary 8-byte string of data. Like it could be a pointer to something in our user land. It could literally be like 4 A's in a row. Like however it's used is however it's used. Like kind of the strength of the interface here is what you're seeing. And so in this case, what we do is we call copy from user, and then we say, hey, this argument is a user pointer. And we are going to copy it into our mode structure. And if we come up to our mode structure, we can see that this is 2 back-to-back ints in memory. So how do we define 2 back-to-back ints in memory? In assembly, anyone know? And I'm going to give this a label. We'll call this mode. So what's our directive?
Data.
Data's 1. I would probably use one that's a little bit easier to reason about, and I will introduce you to .long, which instead of having to reason about byte order, we can just drop numbers in. So in this case, maybe I want to make my webcam, let's see, is it width or height first? It's a good question. So we're width and then height. So let's say we want to make our webcam really high resolution. So let's go 1920 by 1080. I'm aware that it's a little bit outdated for high resolution now, but I don't have 4K memorized, okay? And so we've got our mode, and essentially when we build this out, we can then kind of XXD this out and look at the bottom. So that's what we're going to do really quick. Just because remember, like, because we're not putting this in its own section, it's just going to be essentially stapled to the bottom of our .text section, because that's what we're in. So let's rebuild. And then when I XXD this S, well, I would have to dump out the literal .text section. Let's see. Do I have that object copy? I do. I can't believe that's in my terminal history, honestly. Or it was until my terminal's freezing. Well, never works the way it's supposed to work. Okay, it really isn't like. Okay. Oh, all right. Slightly annoying, but that's fine. There we go. So we will copy out the section of, let's go with S to shellcode raw. And then now we have that. And now if we look at that, we can see that the last 8 bytes are those numbers, just in hex. And similarly, we can also see our string showing up right at the end there as well. All right. And so all we have to do now is just basically supply a pointer to this, because we've said, okay, well, or not there, this tab. Because we've said, okay, well, when we call this ioctl, it's just going to copy from user directly over the mode structure. So we just need to supply a pointer to this. And so we can do essentially the exact same thing we did when we were using our open call, which is just loading the effective address of this. It's just instead of going into RDI, we're going into RDX. And similarly, instead of this path label, we are now going to use mode. So at this point, we've set our system call number, and then we've also set RDI, RSI, and RDX. And so at this point, all we have to do, in theory, is syscall. So let's build that out. And then just to really clearly show what's going on here, if we cat proc and then our webcam demo, it's telling us right now that it's 640 by 480. And in theory, after running this, which we're going to do sudo strace, we can see that we've opened our webcam demo, we've made our ioctl, we've given it this pointer to our data, and now when we cat it out, that state has changed. Yeah, it's cool. Okay, so now we got asked how to debug this process and how to see this in GDB. So let's take a look at that. It's valuable.
It worked.
It did work, but we want to know why it worked. And basically just how to get there. So, and I think I'm going to do this again later. I just think doing this twice is important because I'm going to get asked this question in office hours again. Now, sorry, that distracted me. That was funny. Okay, so essentially, in order to debug in our VM, I come out of the VM. I am in practice mode. So if I hover over this, it says restart in unprivileged because I'm currently in privilege mode, so I can use sudo. And then we pull up VM debug, which essentially is just hooking into the QEMU like kernel that we are emulating. And what we'll notice is that my VM is totally frozen. Like I'm pounding on my keyboard, nothing's showing up because I need to go in and hit continue right here. Now all that shows up. And so the other reason you use practice mode is because we want to know where things are in the kernel. Like this becomes prohibitively difficult when you either have KSLR enabled or you simply just can't get access to this klsims file, which for those of you who haven't watched the lectures yet, there's this magical file called klsims in the proc folder, which essentially exposes the address of all the functions in the kernel. Or sorry, not sudo proc, sudo cat. There we go. So here's all of our kernel functions. And at the bottom right here, I can see here's the webcam demo things that I've set up. So in this case, I named my device, my ioctl function here, just device ioctl. Did you have a question?
Yeah, so like I guess like what's the like the capital T and the lowercase t like between like the address and the actual name?
I actually don't know off the top of my head, but there's an important distinction there.
Yeah, because I was gonna ask like what's the difference between the T being capital and like lowercase? Because like some of the T's are uppercase and some of them are lowercase. Like,
Yeah.
once you define the lowercase, also
So it's definitely not just user defined. Maybe my phone a friend, assistant teacher, co-professor knows the answer. All right, we're doing the research.
Is the brackets debug there? I'm assuming because of the VM debug in the other terminal, or is that?
That's just because it's the device that we loaded. So like everything else doesn't have the like little brackets after it. Yes.
what added the debug there? The VM.
I believe it is. It's not the. I believe it's one of the like proc creation sort of handles. Because if you go look at some of the other pwn.college challenges, it's different. It's not always just debug. I'm not explicitly sure where the string debug comes from, but like it's used to tell the kernel modules apart essentially. So you know, okay, well these are the functions that belong to this guy, and these are the functions that belong to that guy. If you load two different kernel modules at the same time, you'll see them both differently. Do you have an answer?
It appears capital T is global, or lowercase t is a global.
Got you. Okay. That does make sense. Question from the Twitch chats. What? Never mind. I can't read that. Okay. Okay. So basically, proc kl sims contains the address of all these functions. And so when we're in our GDB, we want to be able to look at what's happening in this ioctl function. So I can take this address and we can examine it in GDB. So for example, let's say xi right here, or sorry, I need a hex in front of that. xiox. And this is essentially the start of our function. So we can see that copy to user. There's like the switch statement logic up here. We'll keep going down. We'll see copy from user, essentially representing the two different branches that our device ioctl function has. And so we can put breakpoints in here. So for example, let's do that. So oops, not in there. Let's do break and this address, and then let's continue. And then I'm going to put my other terminal up here. You didn't know this is possible. You can, in fact, put your terminal up top. It's kind of
It's in Tmux too.
yeah, but like, can you do this in Tmux?
Yeah.
Yeah, I know. Anyway, so I do need to trigger that ioctl. So let's do /s. All right, so I started running this. It's presumably opened the device and has now made that ioctl. And then down here we can see, okay, we've hit that breakpoint. And so at this point, we could then step through our function. And basically, essentially just see what happens. But for now, that's just how that works.
Is that a jet thing?
Is that a jet thing? No, this is Vanilla's GDB's thing. So because I don't know why we got a legal instruction. That's interesting. Probably because I'm messing with it, but oh no, it's because I didn't exit in the shellcode. That's why. Okay. But what this is just a different layout for GDB, which likes to break every once in a while. But so one of the things that you can do, which I do this a lot, it's just a little bit slow, is because this VM debug runs as root, like it's essentially equivalent to doing sudo gdb attach. That means it's referencing technically a different gdb init file. So if you've installed gef previously, by putting it in your gdb init file, it's not going to be loaded. What I just do is I'll just come in here and go source opt gef.py, or whatever path to gef.py you have on your local system. Yes.
If I ran sudo vm debug, it would open my file, my GDB file. So that knowledge.
I'm pretty sure it has to do with the way that we've implemented it, specifically in the VM command. Because the VM command runs. Actually, no, that's not the reason. Well, it is because it's implemented in the VM debug command differently. But what I was going to say was false. But essentially, we can source this and then just directly load gef into this little instance. The only thing that you'll have to deal with is that it's going to be a little bit slower. And you'll see what I mean by that really quickly. So let's put that same breakpoint down. Then let's continue. And we're back in. And you can kind of see the latency of it's generating. And then we take another step. And it takes some time. So like, if you're willing to put up with that, that's fine. Otherwise, you can just use vanilla GDB. But personally, I like the creature comforts that gef enables and being able to see like pullback traces. Okay, here's both my threads. Like there's not a lot of confusion left. Got you. Okay, so now, are there any questions on this just like basic ioctl process before I continue on to the other half of the demo? Yes.
Kind of a follow up with the thing I asked earlier about like the T's.
Mhm.
Does that matter in this case? Like, does the local and global stuff matter?
In the context of this class, I would say no,
Okay.
but I can't for certain say no everywhere.
Okay.
There's always going to like the referring back to the very first slide that I presented, like kernel is just kind of complicated sometimes. Like, for example, I'll show up these two funny things just because I find them very entertaining. But you could think of, for example, the heap flow chart. Wait, where is it? This image, yeah. So you could think of, for example, the flow chart of how the heap works. And this is just one component of the kernel. Or you could think of like the kernel diagram that's like on GitHub that is, yeah, this guy. Wait, there's another one that's even better. Hold on. Yeah, this guy.
Oh my god.
So everything above this is considered user space. Everything below this, which is everything you're seeing, is considered kernel. And so you could think of, okay, well, oh, oops. And this is a great resource, by the way, this like make Linux kernel map, because you can click on all these little things and it'll take you straight to like either like the like Bootlin Elixir functions or like wiki pages describing those functionalities. So like I think this is a really cool resource. But like, for example, you could say, okay, we have processes, and then those have threads, and then there's process synchronization, and then process scheduling, and then interrupts, and low level, like down to basically like the CPU's like atomic operations. And so it gets really deep really fast. Like there's a reason that kernel bugs surface up and it's like, oh, this has been in the Linux kernel for like 10 years, it turns out, because there's just a lot of surface to cover. There's also like a very good graph of like lines of code in the Linux kernel that just like keeps exponentially increasing. Okay, so now let's jump to our other demo. Oh, I guess I need to go back here. And so in the second demo, in the second demo that I've set up, what's going on there? We are going to talk about shell coding in the kernel because it's slightly different. And the reason it's slightly different is because when you're in the kernel, making system calls is weird because the system calls go to the kernel. And so how we have to kind of reason about this changes just a little bit. So once again, we're in a kind of similar situation, but this time in our challenge folder, I have a different demo going on. So we have our kernel module that I built, sc.ko, which is going to get loaded in when we start our VM. And then similarly, I have this shellcode demo, which if we open this up, I put W there, but we can see that this is a very, very simple, just essentially another device driver where we have device open, release, and write. And the only thing we care about in the context of this demo is device write, which it copies things from the user into this buffer called shellcode and then calls it. We've seen that before a couple of times in this class. And so very, very basic, just shellcode runner. And so this means that when I boot into my VM, so VM connect, and then I just try to basically yeet random bytes into this device driver. So we'll say like echo ABAB into proc, and this one is called proc shellcode because we gave it this name right here under proc create. So proc shellcode, and we can see that I've crashed my VM because it tried to execute random code. So let's take a look at trying to do this the proper way. And so rather than demo something that's like easily weaponizable into like a challenge solve, we are going to leverage dev TTY and just try to write something to our own terminal rather than do some nefarious purpose. So like you could think of like in the context of these challenges, like privilege escalation, like it's kind of like the classic goal. Like once you're in the kernel, like I'm in the kernel, like how do I make it so that I'm root outside the kernel? Like there's lots of different ways to do it. There's just some lower hanging fruits than others. And so in this case, rather than writing like a .s file and then like doing object copy out to get like the shellcode raw, I'm just going to use pwn tools. So we will just say sc demo, I guess, .py from pwn import star. All right, what's the one line I need when I write shellcode? Context.arch. If you don't have this, you're going to get lots of headaches and just bad times overall. And then we'll define some shellcode. I don't know why that comes up every time. topical. So, and then I guess to finish out the rest of our boilerplate, we're just going to write this to a file. Let's overwrite shellcode raw. That's f. We can say f.write. And then our built shellcode. And then just in theory, we should be able to come in here, write a nop, and run this. So let's see into that class demo. On 3 scdemo.py. Oh, and one other thing that I forgot to mention that's a little bit important, that's a little bit transparent under the hood, is one of the other nice benefits that you get in practice mode is you get to enable KVM in the virtual machine, which basically is this magic flag that makes everything run significantly faster. So you might have noticed already, if you're doing the challenges, that there's a drastic speed difference in the VM between from non-practice and practice mode. That's why. So another reason I would just recommend using practice mode all the time, like until you're ready for that final exploitation push. Robert's shaking his head. Would you like to correct me live? No? Okay. Okay. So in this case, when we want to shellcode in the kernel, it's no longer the case that we can just call the system call open. It's no longer like, instead, we want to use the kernel functions that we have access to through klsims. So, for example, if I grep through for open, we can see there's a lot of different open calls. And so one of the things that you learn over time, just like as a kernel exploiter, is what these functions do. So in the case of what we're looking for here, the way we open a file in the kernel is with this filp open, which essentially gives us a file pointer to that. And so if we go in and look, let's see, where's Elixir open? Another resource that you should get familiar with just for like being a kernel exploiter or someone just in general interested in this is this Elixir Bootlin website. Essentially just contains all of the versions of the Linux source. Very, very useful. So in this case, we can say, okay, I am running Linux 5.4. And so I could go find 5.4 in here. So we'll just go all the way down to the very first one, since that's where we are. And then we can find our symbol. So filp open. And we can find the definition of this function. So filp open opens a file, returns a file pointer. And the two arguments that we need to supply it, or three arguments, is pretty similar to the syscall open. Like it's our file name, it's our flags, and our mode. So things look pretty familiar. And so let's go ahead and try and get that working. So I guess let's do some very minor copying and pasting just to make it so we don't have to flip back and forth that much. Remember that in Pwn tools, you can put comments in your assembly with these with this weird kind of slash block comment C construction, but you can't do it with a hashtag or a semicolon. So this is just the one way that I know of doing it. And so let's go ahead and set this up. So we know that our first argument, our file name, is going to go into RDI. We've already done this once already. So we'll just kind of recycle what we have already, which is this path guy at the bottom. But rather than proc webcam demo, I want to write to my terminal. So I'm going to open dev tty. Just once again, I can echo random bytes into dev tty, and they make it onto my screen. Very, very useful little thing for side channels too. If your standard out is closed, you can write to dev tty, and it still shows up on your terminal. So I can leak that now that the jail module is over. Okay, so now let's get that into RDI. So LEA RDI, and then just another RIP relative addressing. So we'll just call this path. And then similarly, let's see, we need RSI, which is our flags. And I do not want to open dev tty in read mode because we don't want to be reading from dev tty. It just ends up hanging. And so we want to make sure that we're opening in write only, which in this case is our mode of 1. If you didn't know that, you could look up the flags on the man page. Once again, use C types, etc. So let's move RSI and then a 1. Then similarly for mode, I'm just zeroing this out unless I need to think about it, which I don't need to think about it. So zero out RDX, RDX. So we've got our arguments. How do I actually call this function? And so it turns out in order to call this function, I need two pieces or one piece of information really, which is just what's the address of the function. And it's in KLSIMS. Now, this process of finding addresses in KLSIMS works because in this case, kernel ASLR is disabled. If I wanted to have this work like portably, like when KSLR is enabled, I would need to have some kind of leak. So you could think of like a buggy device driver giving you a leak. You could think of basically just the classic ways that this thing kind of happens. Like you put a string in that's too long, it runs up against some data, it's returned to you, like all these fun classic ways that we've gotten leaks over the course of the class. But it's that same process for defeating ASLR in normal processes where it's just, you just need to get a leak and then everything's relative. And if, just to really make sure that that's clear, the offsets to these things, like if you went and literally opened the Linux kernel in IDA, like this VM linez file, that probably won't load in IDA on the Dojo because it's very big, but essentially, let's see, it's like ls opt linux, yeah, VM linux, like this file right here, which that's a symlink to another one. This file right here is essentially our Linux kernel. And so we could go through that, like find offsets, and once we have a leak, it's the same process that you guys have been familiar with up until this point. Okay, but in this case, like KASLR is disabled, so once we find that address once, we never need to find it again. And so we found it once right here, FILP open. And so I just do that, right? Right? Exactly. So this breaks the assembly convention. Like we can't do this. When you write call and then some basically constant like this, it's going to try and do a relative call. Instead, we want to do an absolute call. So, oops. So we have to we have to put this into a register. So we're going to move this into RAX. And then we just simply call RAX. That's simple. And so at this point, in theory, if our shellcode is right, then we are going to be calling this FILP open with the file name, with flags, and with this mode. And so let's go ahead and finish out the rest of this now. So once we've opened this, we need to, once again, get our return value out. So we'll just, I guess I'll dump it into R12 again for now. And then we need to write it to our screen. And there's a few different ways to do this, but the function that we're going to be using is called kernel write. And so if we go back to Bootlin, we find kernel write. So, and the process of finding these functions is about like understanding basically this massive diagram, but also there is, let's see, it's like Linux kernel file structure. There's like a very good man page for this somewhere. I will find it and post it. But essentially there's a very, like, there is a rhyme and reason as to how the Linux kernel is laid out. Like this, like slash, like if you go to slash, like you can see all these different folders, like it's like a standard GitHub repo, like you have like your components sort of split up. And so FS in this case is like our file system, and we find the file in file system called read write. And that contains like our file operations that are basically present across the Linux kernel. Kernel, gosh. So we have kernel read and we have kernel write. So we're going to find those. And so our kernel write function is taking a file, it's taking a buffer, it's taking a count, and it's taking a position. Now, in the kernel, like files are managed slightly differently. It's not just assigned a file descriptor like they are in userland. And so the way that you do this, like in reality, is essentially the same way. You're just saving off your return value that's a pointer rather than just a number. So it becomes harder to guess essentially. But in practice, like we call the open function, we get a return value. That's the thing that we're handing to the next function. Like same process. Just it's a pointer. Yeah, it's a pointer. So Let's go ahead and get that in there just so I don't have to reference it. And then we are once again going to set this up. So rather than moving into R12, like we know that this first argument is going in RDI. So we're just going to move directly into RDI, save ourselves some time. Then we need a buffer. So in my shellcode somewhere, I need a buffer for this, for data to live. Like, and I'm trying to write something, right? So basically I just need a string. So now we can come down here and let's use .string this time. So let's just call this like, maybe not data, that's a bad one. Let's call it to write. So string, oh, did not need to run that. And let's just go hello world for right now. And similarly, like once again, to get the address of this, because like we are passing in a pointer to this buffer. So we're just going to LEA, I think it's RSI, and then we will do rip plus to write. So same process as we're getting our pointer into this open call, just once again, another LEA. Like hopefully this process is looking a little familiar. Like this is why we lecture in C. It gets kind of repetitive eventually, but assembly's fun. So finally, we just have to look at count. And then we have this last little mystery guy that we'll get to in a second for pause. But the count is just how long this is. We could try to dynamically calculate this, or we could just be lazy about it and just say move RDX and let's go. That's 5 characters. That's another 5 characters. Then we have 1 in the middle. And so I'm going to say 12. I just moved that string. Go back. There we go. So we'll just say 12. That should get us everything and including the null item. So then finally, we have this funny guy called pause. And if we go look at how this pause is used, we can see that it's passed into a function. And if we go look at this function, we can see that it is continually being passed into functions. Like one part of the kernel is that everything becomes a wrapper of a wrapper of a wrapper, just makes things convenient to develop. But the point is that eventually we'll get to a place where, okay, I need to make sure that I'm going the right way. There we go. Essentially, we'll get eventually to the place where pause is essentially how far into this buffer you're writing. So you could think of it almost as an offset. And so in this case, we just want to set it to 0. So we will just quickly insert some data. And let's see. So this is an L off T. Now, me, like you, probably doesn't know what an L off T is off the top of my head. Not the AI mode. No. All right. So essentially, L off T is, it doesn't give me the size. That's great. All right. Well, we could write a C program to find out the size. Oh, there you go.
You would technically be
It's a 64-bit version of the type. It is assigned integer type. One down.
No, wait, no, is it said there's one piece in the Linux kernel?
You're so close.
Still
If you're seeing it and I'm not seeing it,
in the description, the third line.
Oh yeah, there we go.
gotcha.
Off T.
All right. So basically, I'm just going to assume that it's 8 bytes is the guess that I'm going to take based off the fact that it says it's a 64, or wait. We're going to try 8 bytes. If it doesn't work, then it doesn't work. So let's just say, let's call this pause. So we'll call this like pause. I was going to say pause position, but like maybe loc. And then let's put a quad word here and just put a 0 there. All right. So there's that data. And then how do we load a rip relative pointer? We've done this a lot. LEA, RCX, because that's where our next argument register is. And then we are going to once again just go to rip plus and then my pause loc. All right. And then now I just need to get my function address into RAX again and then call it. So let's find that function address. So sudo cat proc klsims, and then we are going to grep forward kernel write. There we are. Now there's gonna be a couple of these, but if we go look at the source kernel write, we can see that this kernel write function is essentially it eventually starts to wrap this other one. And so I would recommend using the functions without the underscores in front of them first, unless you really have a good reason to do that. But like, you can dive into the source, you can read the difference. You all are skilled hackers and source code parsers at this point. So if this is something you want to dive more into, you can. And then similarly, we just once again move into RAX. So move RAX, OX this value, and then we're going to call it. Now, there's one last thing that I need to do that's a very important caveat when you're doing shellcode in the kernel. Exit cleanly. And so who can tell me why?
Because of that.
Because it will die. Like, quite literally, it will die. And the way we do this is just very simple, just ret. We need to make sure we get back out of the kernel cleanly. If you try and exit from here, you're going to have a bad time. So instead, we just ret. And the reason this works in this specific case is because I'm calling the shellcode as a function. And so when I ret, because I'm not touching the stack anywhere in this shellcode that I've written, like nowhere am I pushing or popping or like adding or subtracting to RSP, like I'm not clobbering it, it's going to pop that return address off the stack and head back into this device write function and follow the proper chain out. Instead, if you just don't put this ret here, you're going to kernel panic. And we don't want that to happen. Especially because on some kernels, that will just kill the entire thing and cause it to reboot. Like, fun behavior that you have to deal with. And so at this point, we should be able to run this, which, remember, all this is doing is just dumping this into this shellcode raw file. Because I'm running this inside the VM, it's taking a while. I recommend building outside the VM just because it's going to take less time. But in this case, it's pretty short. And then we can look at our shellcode raw. You can see, okay, we've got our hello world, we've got our dev.tty, we've got our bottom like 8 bytes of zeros. And so at this point, we are going to just basically throw it at the device driver. So dev shellcode. Or wait, proc shellcode, my bad. There we go. Oh, all right. Now, I did something wrong because I panicked. So let's see what happens. Happened. So let's get another terminal up. Let's demessage F. What is the demessage argument to keep it persistent? W. There we go. So demessage W. Oops. What? Am I in the
Lowercase.
What? Okay, are you not in the
Oh, thank you. Thank you. There we go. And then now let's see what happens when we try to echo that in. I didn't even save that in my terminal history. Echo shellcode raw. All right, so we did indeed kernel panic. We got a null pointer dereference. So now the question becomes, okay, well, how do we debug this? And so this is the part where we get to start debugging our own shellcode in the kernel, and things get fun quickly. Now, in this case, it's telling me that I am trying to dereference 6, which is interesting. We're going to go ahead and have to look at what's exactly going on there. But let's see. So there's a number of different ways to do this. Like in the traditional shellcode, you would just think, okay, I jam an int3 at the top and go, right? But it turns out that this is a little bit complicated because that int3 is not necessarily passed up to your external GDB instance that's promoted in. So we have to get a little creative with how we set our breakpoints. There's a very cursed strategy that I like to use. There's definitely other ways around this. So for example, let's get back in the VM. So let's proc all sims. And it turns out there's a lot of functions that have the word no-op in them, to the point where there's literally a function called no-op ret. And if we go and look at this function,
So for this website, do we have to use version 5.4?
You don't, but the behavior is going to be different. There might be functions that exist that don't no longer exist in the modern version. There might be I would just recommend using the version that you have, which, as a reminder, proc version contains the version string for the kernel that you're running. So you can always get that information. Otherwise, it's similar to I have this libc version that's blind and I don't know what libc version is, and you can start trying to constraint solve, figure out what Linux kernel version you're on. But in general, just proc version. And note that I didn't need to be root to do that. So yeah. And so in this case, I have this literal function that's called no-op-ret that just returns a 0. It doesn't do anything. And so this means it's a function that I can kind of just call in my shellcode and put a breakpoint on and simulate it in 3. It's kind of painful, but it does work. So if I do move rax, this guy, I need an OX in front of that. And then we're going to call rax. And then let's go ahead and get to our class demo. Run that. And then let's VM debug with this other terminal, which is going to, oh, I'm in the VM. I'm going to wait for this to finish just so I don't have to, there we go. And then so I put that in this function called no-op-ret. And so I can just break there. And then now when my shellcode runs, so we're going to echo shellcode raw into that device again. Oh. Uh-oh. Maybe we died before that. Ooh, do I need to... No, that shouldn't be the problem. Hold on, we got like 5 minutes to figure this out. We can hopefully do it. So let's see. That should be fine. Am I still dying on... Oh, come on, get out of there. There we go. Yes. Let's go with VM Connect. Let's get another terminal in here. Let's get here. Sudo dmessage w. Then that one's going to debug. And then this one is going to go here. And then let's quickly, I guess I don't need to do that. We'll just cat shellcode raw. Oh, I need to put my breakpoint in to the star, what was it? No-op-ret. Keep there. Let's try one more time. And then actually also what I'm going to do is actually watch that handoff from where my shellcode gets executed just to make sure something isn't going, oh, oops, I got to continue there. Something isn't going catastrophically wrong. So I can do pausing and resuming your terminal kind of messes with the terminal emulator, or pausing and resuming the Linux kernel kind of messes with your terminal editor, but it's fine. Emulator, cat. All right, so let's quickly rep for let's see, it was called device right, I believe is what I named it. Yeah. So we're also going to put a breakpoint there just to verify. So there's our 2 breakpoints. And then now let's cat shellcode raw into that device. All right. So now we've broken at the handler. We haven't died yet, so that's good. Let's quickly, let's see, I need to set disassembly flavor Intel because I don't want to look at AT&T syntax. Let's look at our next couple instructions. So let's see. I'm looking to get past that copy from user and to this line right here, which in theory should hand off execution. Okay, so we do get there. And then let's see, let's print out the value of rax as a real value. So 50i. All right, it's looking pretty reasonable. That looks like what I think is supposed to be happening. All right. So now let's SI once. All right. Is it possible that this address is being weird?
Nothing in the kernel is cursed.
Oh, that's right. I did step. Yeah, don't use step instruction. You gotta use next instruction. Gosh, that's annoying. Okay. Which, all right. Oh, hey, we're there. All right, so now we're in our, wait, is it just gonna work now? That'd be really nice. It does just work now. Great. All right, so the curse of, let's call it quantum juxtaposition. We've observed it, so now of course it's working. And so let's exit out of everything to make sure that it's working. So do, exit, VM restart. I'm thinking I might have forgotten to rebuild my shellcode. So VM connect, demo echo into proc. Oh, hey, you know, that's actually probably what I was doing the entire time. Yeah, that has to, okay, hold on. We can confirm this. Ready? So if I do VM connect and then I demessage W again, and then if I echo, yeah, okay, that's exactly what I was doing, was I was just echoing the literal word shellcode raw in, and that first byte, and then it's trying to do something with 6. So, user error. Now, last thing I want to show you in the last 4 minutes is, let's say that I want to do this in a user space process. Like, so I'm in my VM debug. So we'll say VM debug. Let's see how fast I can write a demo for this. So let's say we're in our VM debug, and then I have some file that's doing a thing. So we'll say like thing.c int main, boom, a equals 5, and that's not Python, so we have to give it a data type. Boom, so there's the thing. And then so we are going to go to our, I need to be in the VM eventually. So B GCC thing.co thing. So now I have this file called thing that is an executable. And let's say for some reason a equals 5 was being very painful to me and I wanted to debug it just to see what was happening. So if I get the exact address of, so first off, I have built this as a non-PIE executable just because I did GCC. So when I check sec it, we're going to see that it's non-PIE. One hack that I can do because ASLR is disabled and we're not running processes that aren't position independent is I could put a hardware breakpoint on addresses in this space, which basically says, hey, if anywhere in the kernel this address is hit, break there. And when you're dealing with ASLR, all the addresses are all over the place. And so we can get away with this little kind of tricky hack here. So in here, let's do object.d thing. And then I need to find main, which is going to be way up here somewhere. I should do m equals intel. What is it, like m intel or something? Yeah, there we go. Can't be using AT&T syntax. All right, so let's see. There's main. So let's say I wanted to break on main at 401.106. So because this is the only process that's in this like non-PIE address space, I can come into GDB and instead of using just normal break, there is a command called hbreak for hardware break. And there's a lot of under the hood specifics about how this works. For example, you have a limited amount of hardware breakpoints that you can use because they're literally put into your CPU. But in this case, because we're running in QEMU, it's in like the virtualized like Linux kernel. Long story short, you can do it. And so we can set this hbreak, I hope. I hope. I hope. Hopefully. Hopefully. All right, that's interesting. Info B. Let's try one more time. All right, well, that one worked. Hold on, that's the wrong address though. Del 1, H break. There we go. Don't know why that first one was being weird. But now if I look at my breakpoints, I have this hardware breakpoint at this address. And now in the VM, when I run this program, class demo, I'm going to hit that hardware breakpoint in my user space process. And so if I look at where I am, boom, that's my main function that's setting a equal to 5. And so if you have a really tricky user space program, this is one way to be able to do it in the context of the terminal. It's just that you don't have symbols. Like, for example, it says this is in question mark, question mark. And it's because it really doesn't know what process this is. There are arcane ways to use like GDB scripting to set like conditional breakpoints using the task struct, using PIDs that might get discussed at some future point. But this is a pretty simple way in this environment. What you can also do is just use 2 different instances of GDB, one outside of the VM, one inside the VM. But that's a little painful, but it does work. But yeah, that's all I've got for today. I don't see anyone got any questions before we wrap up. Yes. Because if I try to do this, sometimes it will tell you that that address space is not loaded yet. Like, have you ever gotten like the error can't insert breakpoint because it can't access that memory address? That's why. Basically, it just has inconsistent behavior, is what I've noticed. All right. And then the goal is tomorrow is to hand back your exam corrections. So if you want your exam corrections, or tomorrow, not tomorrow, Thursday, thank you. Thursday, we will be handing back exam corrections, or if you can't make it to the Thursday class, on a Tuesday, I'll give you guys yours back as well.
Do you have any just like last minute tips? In general about the module?
Get started early. Let's see. The first handful of challenges are pretty simple, I think. So if we go just take a quick browse at what we're going to be doing. So I would say up to level 5 is pretty simple. Like this is just basically like what are device drivers? How do we interact with them? Once you get into 6, this is where you're going to start shell coding in the kernels. That's where you're going to have to do those like in like absolute calls with like moving things into RAX, calling around. And then eventually you start to get to basically like KASLR is enabled. Like, okay, now you have to get a leak. Now you have to do all the fun stuff. And then eventually like, okay, well, now I have a kernel device that you have to use like a user space binary to exploit. So you could think of like, how do I do like a side channel across like the kernel user space boundary, like all sorts of fun kind of stuff. But yeah.
So when you do that,